In this lesson, we're going to be talking about directions and angles. To help us understand this, let's draw in a little android that's facing some random direction. Now an angle is just a change in direction caused by some rotation. Suppose for a moment that we had an XY axis pointing in the direction that our little android was facing. If our android turns from the x-axis to the y-axis, we call that a positive angle, because that's the natural direction that you'd rotate in. If it turns in the opposite direction though, we call that a negative angle. Suppose we did rotate the android by some random angle, and we wanted to actually show the angle, we'd do so like this. This funny symbol is the Greek letter theta. Anytime you see a Greek letter, it usually means that we're talking about some angle. Not always, but generally. This arrow shows you the direction that the android turned from its original direction to its new direction. So just to summarize, an angle is a change in direction. Now to talk about angles, we have to have some kind of way of measuring them. I'm going to show you 3 different ways to measure angles that are all useful for their own reasons. So to do this, I'm going to start by drawing 3 circles to represent the rotations. The simplest unit for measuring angles is called the revolution. As the name implies, a revolution involves starting somewhere and then going all the way around the circle to come back to the beginning. There are 2 popular names for a revolution. We can either call it a full turn or a revolution. Just like before, if we go backwards, that would be a negative revolution. It's good to keep this in mind, but let's just put back the original for now. Now, I'd like to make some copies of this circle to show you how some other angles look in terms of revolutions. I'll go ahead and show you half a turn, a quarter of a turn, 3/4 of a turn, and a third of a turn. Revolutions are a great unit to measure angles, but one of their major drawbacks is that they don't always use whole numbers. In fact, if you haven't done a full turn, you'll have less than 1 revolution by definition. To avoid this problem, people that lived a really long time ago decided to divide the circle up into a number of equal parts. So the degree was born. They made a really strange choice, but they decided to break the circle up into 360 equal parts. So a degree is a really tiny sliver that I'm going to draw right now. Of course I wasn't really accurate because it's almost impossible for me to draw this by hand, but this is approximately 1 degree. There's also another very popular notation for degrees that uses a superscript circle, as I'm going to show you now. Now just so you don't forget, a degree is exactly 1/360th of a whole revolution. If you need even more precision, we've also defined a minute and a second. A minute is a 60th of a degree, and we write it like this. And a second is a 60th of a minute, and we write that like this. However, we don't use these all too often, so I'll just go ahead and get rid of them for now. Now the natural question you might ask is, why do we break it up into 360 parts, instead of maybe something like 100 like we usually would? And that's a really good question. Let me just get this circle out of the way just for a minute so I can explain. The truth is, we don't really know who invented them. Sometimes the credit is given to the Persians. We give them credit because this is a drawing of one of their calendars, and it had exactly 360 days on it. However, more commonly, we usually give credit to the Babylonians. Instead of our common number system that we use today based on the number 10, their number system was actually based on the number 60. 6 groups of 60 is just 360. But there's actually a much more compelling reason. We can actually write 360 in terms of these factors. Now since it has so many factors, that means it can divide a lot of numbers. So just to demonstrate this, let me write out all the numbers from 1 to 10. We can obviously divide by 1, and since there's a 2 here, we can divide by 2 as well. Since there's a 3, we can divide by 3, and 2 times 2 is 4, so we can divide by 4. There's a 5, 2 times 3 is 6. We can't divide by 7, but we can do 8, 9, and 10. You can check that all yourself if you like. Now because 360 has so many factors, we can divide by many different numbers and still have a whole number of degrees. Let's just get rid of these pictures for a moment and put back the old picture. Now let's copy all of these circles over and write them in terms of degrees as well. Now half of 360 is just 180. A quarter is just 90. 3/4 is 270. And a third is just 120. Now the last unit I'm going to introduce looks at things a little bit differently. Instead of just randomly chopping the circle up into a number of equal parts, it uses something special about the circle to measure the angles beneath it. The last unit I'm going to show you is called the radian. To introduce the radian, let's start by drawing a radius on the circle. Other than a position, the radius is really the only thing you need to draw a circle. So imagine for a moment that the radius was made of a string, and you wanted to wrap it around the edge of the circle. Let me go ahead and do that for you now. Now this remaining angle is 1 radian. There is actually a problem when you try to use the radius to measure angles, and that's the fact that you can't fit a whole number of radiuses around the edge of the circle, as I'll show you now. As you can see, we fit 6 radians around the circle, but then we have this little piece left over. The fact that it doesn't fully fill the circle is both a strength and a weakness. On one hand, it is really annoying that it doesn't fully fill up the circle, but on the other hand, it allows us to do things that revolutions and degrees just simply can't do, as you'll see later.